This last video for Chapter 8 was inspired by a great homework problem that Dr. Nain assigned a couple of semesters ago. It had to do with a full analysis of a Rankine steam power plant and had to do with determining the entropy production rate of the plant. I found his assignment to be so insightful that and intriguing that I went ahead and solved it myself to see what kind of numbers I ended up with. And boy, did I learn a lot. And so this particular video is a worked out analysis for a basic steam power plant with irreversibilities in the turbine and the pump. And it culminates in an analysis of the entropy production rate of each of the components. And so if you go through this video, I'm going to suggest that this topic is just about graduate level analysis for entropy production rate analysis, as long as we summarize what did we learn from the exercise of this analysis and how might we apply this to a working or a practicing engineering role. So I found it to be extraordinarily powerful. So I'm going to introduce some ideas to you, and I'm going to, as quickly as possible, go through the numerical worked out solution for this problem and discuss the practical results. So, of course, you've got memorized the four basic components of a Rankine cycle, and that's basically what we're going to use in this analysis. But we're going to recognize that the turbine and the pump are both adiabatic but irreversible. And so let's see, what would that? I hope that you are familiar with our basic schematic sketch, where we've got a heat source TH and a heat sink TL, and we've got this black box power plant moving along at a steady rate, putting out some net output power, but we have to purchase the heat added, the rate at which heat is added, Q dot H. And I hope that you're familiar with the temperature entropy diagram of the four components, which each component is doing what. And also you'll see on my TS diagram here, I'm showing that both the turbine and the pump are both adiabatic but irreversible, thus the dashed lines. And so let's do a demo, complete with worked out numbers. So I'll read it for you. It says a steam power plant operates on the Rankine cycle with a steady water and steam flow rate of 250,000 pounds per hour. That would be considered a small to medium-sized power plant. Superheated steam enters the turbine at 600 psia, pounds per square inch absolute, and a temperature of 1,000 F. That's pushing the limits. The condenser operates at a pressure of 1.0 psia. That's a high vacuum with saturated liquid at the outlet of the condenser. Isentropic turbine efficiency is 85%. That's pretty standard. And pump efficiency of 80%, standard. The steam generator furnace is held at a uniform temperature of 1,200 degrees F, pretty standard. And the condenser rejects heat to the surroundings at 70 degrees F. That's just about room temperature. Here's our assignment. Determine the power produced by the turbine, the rate of heat rejected in the condenser, the power required to drive the feed pump, the rate at which heat is added in the steam generator, the net power plant output, that's W dot net, the plant thermal efficiency, and then finally, the hardest part, which dabbles on master's level work, the entropy production rate for each plant component. And I've underlined that because we want to compare. Not only do we want to get the numbers for each component, we want to compare them. And what does this teach us? Okay. And so let's start with the sketch. Let's start with the schematic. And here's the tried and true schematic, of course. And the only numbers I've put on here is that I've got TH, the high temperature reservoir at 1200 degrees F, and TL 7 degrees F. And of course, we know we're going to have to add 460 to both of those to work in absolute temperature degrees R. Well, let's start with a sketch with the equipment layout. So here's my TH, 1200 degrees F, my TL, 70 degrees F, and in between the black box, and we're putting some numbers on top of that. Let's see, we've got M dot, 250,000 pounds per hour, given. We've got the throttle condition of the turbine, 600 psia and 1000 F. And let's see, oh, the turbine outlet pressure, which is going to be the condenser operating pressure, 1 psia. That's all of the data we have. And our job is to do a full thermodynamic analysis of this cycle and then make some conclusions on irreversibility. TS diagram, that's going to be another important part of our sketch. Okay, so um, uh, you're familiar with where all the components are. I've just put numbers to the basic sketch. So here's our turbine throttle condition, 600 pounds and 1000 F. Let's see, I've labeled the condenser pressure. P3 equals P2, and it doesn't look like I have 1 psia. I don't think I've labeled that there. Here's my 600 psia is my feed water pump outlet pressure. So this is a very good bona fide TS diagram that we will need to do our analysis. So we'll have to refer back to this, at least in our heads, on what we're doing when we're putting pencil to paper and getting numerical results. Okay, where do we start? Well, we start at the turbine. Let's analyze the turbine, which for this one is going to be, let's see, it's adiabatic but irreversible. So the first thing we will do is analyze the isentropic turbine, Let's see, for isentropic turbine, S2 equals S1. I've looked up the property at my throttle condition, okay? And then I've also written down SG2 and SF2 because I have a sneaky suspicion that the outlet state 2 is going to be under the dome. So I solved for, yep, and it is. I solved, so S1 is 1.715, SG2 1.98, yeah, under the dome. So I solved for the quality 2I. X2I is about 86% quality. Why did I do that? Because I need to find H2I. I need the quality to find H2I because that's going to give me W isentropic of the turbine. So H2I, using the definition of quality, 958.47 BTUs per pound. And let's see, H1 was the lookup, 1517.8. And I run through the numbers to get W isentropic. W dot over M dot is 559.3 BTUs per pound mass. Okay, so that's the isentropic turbine. But wait a minute, I know that I've got the isentropic turbine efficiency of 85%. Let's see, I remember what the definition of turbine efficiency is. It says that W actual is going to be 85% of the isentropic, or 475.4 BTUs per pound mass, W dot over M dot. Okay, let's see, WH1. So I need to use the first law to solve for H2 actual. Let's see. Let's see, Qn, that's 0, minus W actual equals H2 minus H1. So I can solve flat out for H2 actual is H1 minus W actual. And so we've got 1042.4 is H2 actual. Why did I even need to do that? Well, let's see. Because I've got W actual to get the turbine output power, I just multiply this by 250,000 to get the actual output power. The reason I need H2 actual is because I'm looking ahead to analyze the condenser process. Okay, so let's see. Looks like, okay, so just as I said, W actual, we determined from our analysis and applying turbine efficiency. M dot is given. So W dot is this huge number of BTUs per hour. And so I've got to go look up a conversion, and I see that in my conversion lookup, I've got 3,413 BTUs per hour equals 1 kilowatt. So I'll solve that I've got 34,825 kilowatts of output power. But look, that's enough to reduce down to reduce to megawatts. If I divide by 1,000, I've got a actual turbine output power of 34.8 megawatts. And I wrote out turbine is producing 34.8 megawatts of power. Okay, we're well on our way. We're really into our analysis now. Condenser analysis. Let's see. We'll apply the first law to figure out the heat rejected in the condenser. So let's see. For the condenser, Q dot N, that's going to be Q dot L, minus W dot out is equal to M dot given times H3 minus H2 actual. We just found H2 actual, okay? We are going to get a negative number here because H3 is going to be a much smaller number than H2 actual. Let's see. H3 is 69.74. That was going to be, what did I do? I looked up that value as H sub F at P2 at 1 PSIA. So that's a lookup value, 69.7. So I do the math to see that the heat added in the boiler, heat added, is negative 2.43 times 10 to the 8th BTUs per hour. Okay, and so the negative sign, that makes sense. And so the condenser is rejecting heat from the steam at a rate of 243 times 10 to the 6th BTUs per hour. So you see, I wrote out my result instead of saying Q dot N was negative, blah, blah, blah. Okay, so I've got a good handle now on how much heat is being rejected in the condenser down to TL. Now we got to calculate the power required to drive the actual pump. First thing we'll do is analyze the reversible pump first. And so remember, the key analysis part of the feed water pump is recognizing that the working fluid is incompressible. So V is constant. And so the reversible work, W dot over M dot for the pump, is going to be, well, negative minus the integral of VdP. We pulled V out of the integral since it's constant. And so we've got W reversible is minus V3 times P4 minus P3. So we're going to get a negative number and determine what that number is. We'll turn the crank on the next slide. Oh, let's see. How do we get V inlet? V inlet is simply VF at T3. And for our case, we know that we've got a saturated liquid at a known pressure. And so we'll look up V sub F at 1 PSIA to get V, little V3. Yep, sure enough, that's what we're doing. Okay, so M dot is given. We've got P4 and P3 in pounds per square inch absolute. We got to plan ahead and transform that into work usable units. V3 equals V4, and that's a lookup. That's going to be V sub F. Since it's saturated liquid, it's V sub F at 1 PSIA. I'm looking ahead. I've got to change my pressures to pounds force per square foot. So I multiplied both of these by 144 to get my pressures in pounds per square foot. So I'm going to turn the crank here. My W reversible, it's going to be a negative number. And remember, it's going to be V3 times P3 minus P4. Negative number. Well, it's 1,392 negative foot-pounds force per pound mass. I got to get into BTUs per pound, so I'm going to look up or remember my conversion. There's 778 foot-pounds force in 1 BTU, so therefore I'm going to take this number divided by 778 to get the reversible work is negative 1.79 BTUs per pound mass. A pretty small number, right? But I do know I'm going to need a little more than that to actually drive the actual pump. I remember my definition of pump efficiency, so I'm going to take 1.79 divided by 0.8 to bump up the work required, negative 2.24 BTUs per pound mass. So that's little w, W dot over M dot for the pump. Actual work, W dot over M dot. Okay, so we've got little w. Let's find W dot actual needed for the pump. All right, and so here it is, negative 2.24 BTUs per pound. M dot is given, 250,000. And so let's see, we've got so many, well, we multiply these two numbers together to get this huge number of BTUs per hour. But remember, I'm going to need to go to kilowatts or megawatts. So I've got to remember my conversion. 3,413 BTUs per hour equals 1 kilowatt. So I'm going to divide this monstrous number by 3,413 to get the pump output power is negative 163.8 kilowatts. And so I'm going to change that to megawatts to compare with my turbine. So I'll move the decimal place 3 places to get the pump output power is negative 0.16 megawatts. Wow. So I've written out in a sentence the power and the amount of 164 kilowatts is needed to drive the pump. Make it clear what we've got. And then in my green text box, let's look at this. The turbine output power is 34.8 megawatts, and it only takes 0.16 megawatts to drive the pump. That is a bargain in terms of net output power. So do you see that by far and away, your turbine output is nearly going totally to the customer by way of electric power. Okay, so very little back work is needed to drive that feed water pump. It's kind of amazing. Okay, boiler. Okay, so now we got to figure out Q dot H, what we've got to buy to run this power plant. Okay, and so remember that in terms of dividing the first law by M dot, we've got QN. I'm sorry. I'm sorry. I got to run the tape back. We need H4 actual before we do the boiler analysis. Okay. We got to figure out what is H4 actual. And so, yes. And so here, what I'm circling here does not have anything to do with the boiler. This is the first law of the pump. Qn of the pump minus little w out of the pump is H4 actual minus H3. So I can solve for H4 actual. I need that for my pump analysis. So H4 actual is H3 minus W actual of the pump, which was a negative number. And so I'm going to get a bigger number here for H4 actual. And that's this work down here. Okay, here's W actual, BTUs per pound, negative 2.24. H3 was 69.74. I've already looked it up. And so H4 actual is 71.98 BTUs per pound. Now I can go to my boiler analysis, which I've written out here. Getting a little ahead of myself. So Q dot N, that's going to be Q dot H for the boiler minus W dot out. Well, that's 0. Boiler's not lifting a weight. Is M dot known times H4 actual minus H1. Now, that is not right. So that is a typo, isn't it? Okay. So look, I have swapped my inlet and outlet enthalpy. So don't blindly copy down what I got on the slide. For the first law for the boiler, Q dot N minus W dot out equals M dot times H leaving H1 minus H entering, H4A. So be very aware of that. That's a typo. Wow, very careless on my part. At least my observation is right. QN is going to be positive for the boiler. Okay. Let's check our work. Let's be sure I got my numbers right here. And so this is also incorrect. This would also a typo here. Ooh, at least in my Excel solution, I got it right. So gosh, another careless error. I'm going to have to correct this PowerPoint when I quit doing the video. Qn for the boiler equals M dot times H1 minus H4. 1 is leaving the boiler. 4 is coming into the boiler. And so thank goodness my Excel solution is good, right? M dot given. H1, we already looked it up. H4, we just determined it. And here we go. And so my first law in my Excel version, okay, we've got M dot times H1 minus H4A. Here's my numbers. Yeah. And look, I've got this huge amount of Q dot H and BTUs per hour. So I had to do some studying to say, in my sentence, heat is added in the boiler at a rate of 361.5 times 10 to the 6, in other words, million. 361 million BTUs per hour is the heat transfer rate into the boiler. So please excuse my typos on the PowerPoint. Very careless of me. Now we can get the thermal efficiency of the power plant. We've got it all. The net plant output power is simply the turbine output minus the power required to drive the pump, or 34.66 megawatts. There's my work shown there. Okay. That's the energy sought, the energy that costs. We just got Q dot H for the boiler. So now we've got all those numbers. So the thermal efficiency is, W dot net divided by Q dot H with our units all straightened out. And so our thermal efficiency, 32.7, a respectable Rankine cycle thermal efficiency, 32.7%. Power plant thermal efficiency is 32.7. Okay, we've done the undergraduate level, analysis. Now what we want to do is we want to study entropy production rate and compare the results. So let's look at a generic steady state, steady flow open system. Doesn't have to be a turbine. It can be any open system. I just picked this picture, okay? And I've said, okay, I've got any open system, inlet state 1, outlet state 2, output power and heat transfer rate in from T of the surroundings. So that's my basic sketch for this statement of entropy production rate. And so without deriving it, of course, we go back to chapter 6 to see that sigma dot, the rate of entropy production, that's why I got the dot over top of it, is minus the sum of the heat transfer in divided by the temperature at which it's transferred, plus the sum of the m dot leaving, s leaving, minus the sum of the m dot in, s in. So that's our fundamental governing equation for calculating the entropy production rate for our 4 basic components. And then we're going to numerically evaluate it and compare. Okay, the actual turbine. Let's work on the actual turbine first. So sigma dot for the turbine, it's minus Q dot over T. Turbine, fully insulated. I'm going to lose that term. Woo! One inlet, one outlet. So I've got M dot. Thank goodness I got my S leaving the turbine minus S entering the turbine. That's going to be greater than 0. So let's go through the numbers. And so sure enough, let's see. I had to go back and find S1. That was a lookup. We already had that from previous work. So S1 is from previous work. I need to find S2 actual. How do I do that? Well, I wrote down X2 actual. I found that from previous work in the turbus analysis. I wrote down SG and SF, so I applied my definition of quality to get S2 actual is 1.8649. Crank the numbers to get sigma dot of the turbine is 37,356 BTUs per hour degree R. 37,356 BTUs per hour degree R. That is the measure of irreversibility rate associated with the turbine. Now let's switch over and do the pump because it's going to be very similar. Sigma dot, entropy production rate for the pump, minus Q dot in. Pump is insulated. That term goes away. Plus M dot, okay? And sure enough, the pump outlet is S4A. Woo, thank goodness. Into the pump, S3, yes, okay? And so I see that, let's see, I need S4A. Gosh, how do I get that? What I did there was, let's see, I saw that I've got a compressed liquid. And so I'm gonna tabulate. I have H sub F is 71.98. So I determined that from H4 actual. And so I did an interpolation to determine S4 actual based on the enthalpy, and I've got 0.1366, S4 actual in the compressed liquid region. Okay, that's going to be SF at the temperature of the pump outlet, which is 103.9. Okay, so that's a little subtle, and that's what sort of makes it graduate level a little bit. But to go through the numbers now, M dot given, S4A, I just found that. S3, that was a lookup value. S sub F, okay? And so sigma dot for the pump is 971 BTUs per hour per degree R. So we're halfway there on our entropy production rate. Let's go to the condenser, okay? What do we got here? We have to include our Q dot term here, okay? So we've got sigma dot and we've got flow in and out of the condenser. So we've got the full expression to evaluate here in the condenser. Sigma dot of the condenser is, now remember, Q dot in the condenser is a negative number. So I've got a negative sign and a negative number, so they're going to cancel, divided by TL. Let's see, look at my low temperature. I'm careful to be working in degrees R. I changed 70 degrees to degrees R, M dot given. Let's see, S3, that was a lookup. Okay, that's SF at P3. I know it's a saturated liquid. And S2A, I got that from above, okay, in my turbine outlet analysis. And you're right. And so that's 1.8649. I needed that for my turbine irreversibility rate analysis. I already had that. So I turned the crank on my numbers, all these numbers, and it turns out to be 25,729. A positive number makes sense. So far, I've got 3 positive numbers. Woo, thank goodness. That says that all of these proposed processes are possible, right? And so the entropy production rate for the condenser is 25,729 BTUs per hour per degree R. Now we got to go to the boiler and we'll be finished. Okay, same approach on the boiler. We've got to evaluate all of our terms because in our boiler, sigma dot of the boiler, I've got heat added. I've got a positive number here. So minus a positive number divided by a positive number. Positive. I've changed my temperature to absolute temperature, degrees R. M dot, I've got it. Okay. S1, I've already looked it up. S4A, I've already determined that from my pump analysis. So I turn the crank to get sigma dot for the boiler is positive 176,985 BTUs per hour degree R. So the entropy production rate for the boiler is that much. Okay, so we got sigma dot for all 4 components. They're all positive. That's great. That makes sense. That's good common sense. They'd all better be either positive or 0. Okay. Now let's compare. All right. So let's go and look at the whole problem solution results. Power produced by the turbine, 34.83 megawatts. Okay. The rate of heat rejected in the condenser, 243 million BTUs an hour. The power required to drive the feed water pump, a small number, 0.16 megawatts. The rate of heat added in the steam generator, 361 million BTUs an hour. Okay. The net plant output, simply add these or just subtract the power required from the turbine power, 34.7 megawatts. The thermal efficiency of the power plant, 32.7%. And now let's look at our entropy production rates in BTUs per hour degree R for our 4 components. Okay. Turbine, that amount. Condenser, that amount. Pump, that little amount. And boiler, that big amount. So 2 things to observe, 2 things for me. I say, wow, that's a big practical conclusion. And that's something to think about at the graduate level. And planning about being a practicing engineer. If your job was to reduce irreversibility, okay, if your job was to improve net plant efficiency, where might your efforts be best spent? By doing an entropy production rate analysis, that shows you that your efforts, your engineering efforts, would probably be best spent focusing on the boiler process, because by far and away, look at how these numbers shake out. By far and away, the boiler entropy production rate is more times more than any of these components. So that's step 1. The other practical conclusion is if you are charged with improving efficiency of equipment. How about equipment efficiency? Where would your, if we said, if your boss said, I want you to work on the turbine and the pump and improving the turbine efficiency and the pump efficiency, where would you get the most bang for your engineering efforts in terms of reducing entropy production? It's neat to quantify this. I should spend most of my engineering time figuring out ways to improve the turbine efficiency more than improving the pump efficiency, because there's so much more entropy produced by this turbine compared to that pump. And so that's another very valuable practical conclusion as you're planning to be a practicing engineer. And so that's what makes it dabble at the, say, the master's level level of difficulty, because it's not easy to determine entropy production rate. There's for some very subtle situations. Undergraduates should be able to muddle through, but probably would take a significant amount of time. So I hope that working through that example problem all the way through, doing a full, pretty quick analysis, helps you see how to go through a full power plant analysis quickly. Of course, I had all the numbers looked up, right? I didn't have to do that live. And then adding to a traditional power plant analysis, that entropy production rate analysis, that can really help distinguish you or differentiate you from your engineering peers when you're just starting out as a new engineer. So doing a entropy production rate analysis, that can help put you on the map. So I hope you got something out of that. That concludes the videos I have planned for Chapter 8. So it's on to Chapter 9, where we totally switch gears, other than we continue to look at systems operating in a cycle. But for Chapter 9, we're looking at ideal gases and not phase change substances. See you then.